So right now I'm going to work out the first step in a series of different equilibrium problems. So the first question I'm going to do has to do with writing the equilibrium constant. So what you're going to do is you get a reaction here, like this, and they're going to ask you to write the equilibrium constant, which is going to be the same no matter what reaction you get. So you put your little divider line first, and you're going to use brackets, and then the top part, it always goes the products. So we're going to write CO2 in a bracket. Then on the bottom, another bracket, we have CO, bracket, and then we have O2, and you're going to close the brackets. Once you have that, you can go back and add your coefficients. So there's a 2 in front of CO, and it's going to go as an exponent. And then there's a 2 in front of CO2. So you put that exponent there, and all of this is equal. And so they're asking for just a constant. That's all you have to do. There's no math involved. It's just setting up the equation. So in the last video I showed you how to set up equilibrium constant, and now we're going to use that for question 7.56 in the book, chapter 7. And in the question it says, for the reaction N2O4 that becomes 2NO2, the equilibrium concentrations at 25 degrees Celsius are 0.0325 for NO2 and 0.147 for N2O4. And it's asking what is the value of K, which is our equilibrium constant. So the first thing you're going to do is set up the equilibrium constant that we did in the last video. So it's going to be K equals NO2, and there's 2 of them, over N2O4. Which, if then you plug in the values that they give you in the question, so that becomes 0.0325 moles per liter squared over 0.147 moles per liter. So your units are going to cancel out because K is a unitless number. So then once you do the math, you're going to square the 0.0325 first, and then divide by 0.147, which gives you a number that is 0.007185. But we start with 3 significant numbers. So you need to put that into scientific form, which would be 7.19 times 10 to the negative third. The last part of the question that they ask you is if this reaction favors reactants or products. Since this is a negative number, we know that the reaction equilibrium is to the left, which means it's going to favor reactants. So the next set of problems we're going to work on is we're going to talk about the Chatlier's principle. Excuse me if I said that wrong to all you French people out there. So pretty simple. We got a reaction right here talking about oxygen converting to ozone. And this is going to be number 7.62 in your book, chapter 7. And it gives you our enthalpy and our equilibrium constants. So for enthalpy, we have a positive 68 kcal per mole, and our equilibrium constant is 2.68 times 10 to the 29. And then this question asks you a series of questions. The first one being, is this an endothermic or exothermic reaction? And in order to figure that out, you look at your enthalpy value. It's a positive 68, which means that that this reaction is absorbing energy in order for it to produce ozone. So the heat is over here on this side. And if it absorbs heat, it means it's endothermic. Then it asks if this reaction favors reactants or products. You go down to your equilibrium constant and you see this huge negative 10 to the negative 29, which means that this is almost all reactants. Then we get into more of the Chatlier's principle, and it asks you, if you look at this reaction and you throw different stressors on it, what's going to happen to your equilibrium? The first one being is if we increase the pressure by decreasing volume. Now, the big thing you look at, you're going to increase the pressure here, so it's going to compress the volume, which causes that, this reaction has to stay at equilibrium. So if something happens to here, it's going to favor this side because there's pressure, 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 so we want to send some of this pressure to the other side to equal out. So we'll send pressure here, it'll kind of go back and forth until it gets to equilibrium again. So if you do something to this side, it's going to favor the product side, or in this case, the ozone side. So that's the question answer to question C1. So C2 asks, if we increase the concentration of O2, what's going to happen to the equilibrium? So if we're going to throw more O2 at this, to balance these out, we've just increased the concentration. So the scale is heavy on this side. So again, we're going to favor the ozone side because we want to send some of the concentration, some of that weight away. We want to have this balanced again. So it's going to, C2 is, again, we're favoring the products or the ozone side. 3 says if we increase the concentration of ozone, or O3, what's going to happen? Well, same thing as the last one. Now we have all this extra weight on this side, so we have to go back, we have to send some of it this way. So it means that we're favoring the products or the O2, the oxygen. And that's C3. C4 says if we throw a catalyst at this, what's going to happen? Kind of a trick question. Catalyst has nothing to do with equilibrium. Catalysts only affect the rate of a reaction, so it makes the reaction happen faster. So it has no effect whatsoever on equilibrium. And then the last one, C5, says if we throw some heat at this, we increase the temperature, what's going to happen? Well, we know from our enthalpy that this side already has heat. It's the same as saying heat plus 3O2. So if we add more heat to this side, we got to get rid of some of that heat. We're going to throw it to this side. So it means, again, that we're favoring ozone or our products because we already have heat over here. Now we need to get rid of some because we're adding extra. And so that's the kind of the idea behind this guy's principle. It's basically saying whenever you change the environment or add stress to one side of a reaction, it has to be balanced out by the other side.